Good morning. This is Boaz Arberg, and today's discussion will be robot dynamics. We'll take a look at physical environment of a robot. We'll look at its kinematic diagrams. We'll define its coordinate system. We'll define its variables. We'll define the problem, and we'll look at the general solution to a dynamics problem. Here's an example of an articulated robot. What you see here that the robot has a revolute joint at the base. It has another revolute for the first link and another revolute joint for the second link. It has a gripper with a few degrees of freedom there and a tool center point which holds the part. If you look at the description of this robot in kinematic diagram, we see similar description with revolute joint for the base, revolute joint for one arm, revolute joint for another arm, tool center point, and also we have some reference scale to determine the size, general size. We call this robot triple R, which is standing for revolute, revolute, and revolute. The kinematic diagram is showing an inertial frame, x0, y0, z0, fixed to the base. It shows an axis x1, y1, and z1, which is rotating with respect to x0 in the direction of z0, a certain angle, and this is the yaw. And then between x1 to x2, we have a pitch angle, and then this represents x2. And then in coordinate system 2, we have not only x2, but a little bit offset. We have the coordinate origin of system 3, where the axis is along the link, and z and y are shown over here, right-hand coordinate system. And basically, this is the representation of the robot coordinate system. Over here, we see a different view to get oriented, pretty much a front view of the same configuration. To simplify the definition of various variables, we remove the robot and show just the coordinate systems. And here's an example of how it may get complicated to describe the various parameters and variables. We like to define the kinematic variables, position, velocity, acceleration. Over here we see the position theta 1, theta 2, and theta 3 of the angles that we saw earlier, as well as their derivatives, velocity and acceleration for each one of them. We like to note the positive direction of these variables. The theta is positive in the direction shown because it's rotating x0 towards y0 in a direction of z0, which is exactly the right-hand rule of a right-hand screw. However, if you look at x2 is rotating in a positive direction of of y2 as shown, but it is actually an opposite to the right-hand screw. It will not advance the right-hand screw in this rotation, as shown here with this arrow, will advance in the other direction. That's why we have a minus sign here. And in this case, where we're showing a positive rotation in this direction for going from x2 to x3, it is going again in a positive direction of y2, and this is the right-hand screw. We move in this direction, and the screw will advance in the direction of y2. Other parameters that we have over here is various position vectors such as R1, R2, R3. You see, to get to the tool center point, we have this vector 1, R2 plus R3. They are oriented in space, each one in its own coordinate system, can be easily defined, and we also have, in a similar way, the definition of position of the center of gravities. Finally, we need the inertial parameters of the system, such as mass of link 3 and mass of link 2, and the inertia of link 2 and inertia of link 3. So these are the parameters, and let's take a look at the problem definition. In general, what we're looking for is the robot is doing some work, and it has some forces and loads on the gripper, and we'd like to know what are the required motor torques in each one of these joints and the reaction on a bearing in order to do some sizing. So find the required joint motor torques and resulting joint forces and torques reactions for a given load and robot parameters. The robot parameters, as we saw, are size, inertia, and motion, and the loads are the gripper force and the gripper torque as a result of the work that the robot is doing. Now, in order to find the solution, we have to start looking at the free body diagram of a typical link. We see a typical link here. This link has a center of gravity. It has two joints. This joint is where link 0, neighboring link, is acting on link 1. We call this one link 1. This joint over here is either connecting to the tool center point or to a neighboring link, which is link 2. So the solution involves in first setting up the dynamic equations, and we have two sets of equations for each link. One is the linear equilibrium of forces for this link. The other one is the rotational equilibrium of moments. Now let's take a look at the summation of forces. Now, the forces that act on this link is F01, the force that link 0 acting on 1. We also have, similarly, F21, the force that link 2 is acting on link 1. These are these two guys. Then we have acting at the CG an inertial force, and we have acting on the CG a gravitational force. So we have these four forces acting on link 1, and the equilibrium equation sets them to 0. Now, the inertial force is equal to minus m1 times the absolute acceleration of the CG of link 1. This is so-called Dalamet principle. We take Newton's law, F equal ma, we plug it into the summation of forces equal to 0, and we treat it as just a static force with a minus sign here. The gravitational force is m1 times the gravity. And this basically is one equation. The second equation is the Euler rotational equation. It's similar. We take the summation of torques about the CG equal to 0. It's a little bit more complicated, but let's take a look at the details. First of all, we have the torque that link 0 is acting on 1. This is the torque that link 0 is acting on 1 through joint 1. Similarly, we have the torque that link 2 is acting on 1. This is the link 2 is acting on 1. It could be the gripper, but for now, let's just assume that it's another link. Then we have the torque that this force is acting on the CG. Force 01 has a radius vector from the CG to the point of application of the force. Now, this vector over here, you see, is equal to the minus of R1 plus R1 CG. So the reason why it's minus is because the sum of these two vectors will be a vector from here to here. But we're interested in a vector from the CG to the point of application of force. That's why we have this minus sign here. And we have to cross it with this force over here. Similarly, we have a vector from the CG to the point of application of this force, and this is minus R1 CG. So that's why we have a minus sign here. Very important to remember that. And we have to cross it with this force. And finally, we have the torque of the inertial torque that has to all sum up to 0. Now, the inertial torque has two components. The inertial torque basically is the rate of change in time of the angular momentum. The angular momentum equals to the moment of inertia times the angular velocity. So if we take the derivative of this expression, the first term will be the moment of inertia times the acceleration, and this term is over here. Moment of inertia, I of link 1, times the absolute angular acceleration of this link is equal to the inertial torque, as we usually know it. Another term which is not that familiar with is the second term, where we take omega, the rate of change of velocity, the rate of change in position, velocity of this link in space, and we have to, absolute velocity, and we have to cross it with the momentum, because the momentum may change direction, and therefore it has to be taken as part of the derivative, as we saw in earlier presentations. And we call this particular term the gyroscopic torque. So this is the total inertial torque, and we have to remember to put a minus sign when we plug it in here. So to get a solution, we would have to take the equation of summation of forces, and the first thing that we want to do is to solve for the unknown force, which is over here. We know these forces because they're coming in from previous solutions of previous link. We're starting with the one that is engaged with the gripper, where we know the forces and torques, and then we come down to find the reaction torque and reaction force. And once we go through the chain, this will be known, and what we'll be looking in this particular case is for F01, for this particular force here. So what we do, we solve for it from this equation, and this means that we have to take everything else to the other side with a minus sign. So we take, this is minus F2, and this is minus F inertial, but we remember that it has a minus sign here, and this is minus the gravitational force. So then we take care of this, we remove this, you see that this term becomes plus. So we have to be careful with this. So we go step by step and eliminate these redundant signs to end up with the final signs for all these terms. Now, similarly, if we want to solve for the torque of the of this neighboring link on the link of interest, then what we have to do, we have to take this equation, Euler equation, and solve for the torque of interest. So this is the one. And then everything else is moving to the other side with a minus sign. You see, we're taking T21 with a minus sign. We're taking this whole expression with a minus sign, and we have to remember that it was before a minus sign. So it's minus minus. We have to take care of that. Again, we have minus minus, and then the inertial force, we have minus, and again, two minuses. So when we add them all up and we take care of these duplicate minuses, we get minus T21 and these two minuses will become plus, and these two minuses will become plus, and then over here we'll have pluses. So this will be the only minus sign after we convert it to the other side of the equation. Now, this was for one link. The general solution for a robot with n links will be n times 2 sets of equations, one linear and one rotary for each link. So what we have to do is to just keep on going through the chain from the gripper to the first link, find the reactions, then knowing this reaction, go to the second link, find the reaction, and then go to the base and find the reaction. But when we do the solution for a link, we have to keep in mind that all the vectors which are engaged in that particular equation must be resolved to components in that coordinate system. You see, this link 1 has its coordinate system, and everything, all the vectors here, no matter where they're coming from, this guy may be coming in from a different coordinate system, we have to use the transformation matrix to resolve it to these coordinates. Otherwise, we will end up with an error. So here's an example. Just took one example. The Newton's equilibrium equation with the solution, F21 was probably represented in coordinate system 2, this force over here, when it was solved. But now we have to use it in coordinate system 1, therefore we have to hit it with a transformation matrix from coordinate system 2 to 1, a vector which was represented in coordinate system 2, and this will bring it as a happy camper in this equation, and it could actually be added and subtracted to all the other components which will be represented in coordinate system 1. Now we have here an absolute acceleration of the CG, and this also must be in coordinate system 1. But when we look at its expression, then we can see that the absolute acceleration of this point is equal to the absolute acceleration of a reference point, and let's call this joint 0, 1. So this is the absolute acceleration of the CG in coordinate system 1 equals to the absolute acceleration of joint 1, okay, when it was actually presented in coordinate system 1. That's where we calculated it. And then we have to hit it with a transformation matrix from 0 to 1 in order to be a happy camper over here in this equation. Otherwise, this coordinates is not going to add up to the other one. And this is an example of how we do that. Now, when we talk about this particular transformation of omega, omega 1 is the absolute angular velocity of link 1, but it is equal to the sum of the two relative velocity, one velocity of 0, 1 with respect to inertia, and one velocity of system 1 with respect to system 0, which is omega 1. Remember, theta 1 was the angular rotation of coordinate system 1 with respect to 0. So omega 1 is a relative angular velocity. So we have to take this omega 0, which was probably conveniently represented in coordinate system 0, and hit it with the transformation matrix from coordinate system 0 to 1. And similarly, we'll have to do it. So you see, these things get a little bit complicated, and the only way to get through is, number one, to be careful with carrying over all these signs, and number two, at the end of a solution, we like to check it graphically to make sure that everything is correct. And many times with the graphical solution, you find mistakes. So in conclusion, the general solution of robot dynamics problem includes drawing a kinematic diagram which has all the degrees of freedom, defining coordinate system for the joints and links, define variables and parameters, write 2n Newton and Euler vector equations, n is the number of degrees of freedom, add to each equation all the required transformations, define how the transformation matrices will look like, and then solve these equations one at a time using computerized tools such as MATCAD that we saw before in a previous presentation, or MATLAB, or C++, or C++, Excel, etc. And finally, check the results graphically with a CAD system just to make sure that there's no errors in a presentation of the solution. So this pretty much concludes this presentation, and in upcoming presentations we take a look at some example problems. Thank you.